So now we're moving to the sort of analysis stages. So this is taking those images that we've been able to produce and turning them into something that we can do science with. So the first step in that process is the PSF subtraction. So this is that step I mentioned earlier, where we have that residual light from the star, and I can actually just remind you briefly of this, just in case you're not quite in the loop. And that's, we have this image that we've done most of the cleaning on. There's some starlight here, and we want to subtract that away and see, is there any planets underneath? So before I touch on that, I do want to come back to the MIRI glow stick. So for MIRI, we have this really, really bright glow stick feature that predominantly occurs across the 4-quadrant phase mask edges, and particularly this one roughly horizontal edge here. Now, this is being produced. We think there's some component. I'm sure someone on the call knows precisely which one, that has some temperature that's above the temperature of the telescope mirror and the optical elements and the whole instruments themselves. But what happens is the light, that heat from that bounces off of the sun shield itself and scatters into the optical instrument. And when it hits the 4-quadrant phase mask, because it has this slight offset in physical space, we get a scattering effect at that edge, and that produces this really, really bright glow stick feature you're seeing here. So the way we account for this, unfortunately we can account for it, is to take our target observation as normal, and then afterwards, preferably close in time, you point at an empty, quote-unquote, empty region of sky to calibrate that glow stick feature so that you can just subtract it away from the observation. That's what we did for that paper on HIP 65426b that I linked in the Slack channel just a second ago. And this is how that kind of looks, So I've changed the scaling here a little bit now just so you can see the residual stellar light. But on the left is the unsubtracted, so with that glow stick feature fully there. And on the right is after we've performed that median background subtraction of that glow stick feature. And you can see that glow stick is enormous, and it really does dominate the image. So this is a very, very vital step in terms of being able to dig out this residual stellar light so that you can perform PSF subtraction. Okay, so for NIRICam or for MIRI, we need to subtract. So I showed you that image earlier. We have these kind of pictures of what the images look like, and we want to dig underneath that bright, bright light in the middle to see if there's any planets there. In the case of HIP 65426b, we know there's a planet there, but for other objects, maybe you don't know ahead of time, and you just want to go digging for treasure, essentially. So I mentioned earlier, there's a few ways to do that. You can do it with this angular differential imaging or reference differential imaging. spaceKLIP can handle both situations. And it does that using pyKLIP. So for those who aren't familiar, pyKLIP is this library that does a whole ton of PSF subtraction and high contrast data analysis procedures. So in our case, we take our target and we have a ton of images, all these different integrations that I mentioned. Then we get our reference images, and these could be some of the target images themselves at different roles, or they could be images of a reference star. And then pyKLIP can kind of digest all of that, scale the images appropriately, and perform an optimal subtraction of that residual stellar light, and you get an image like we see on the right. So you can see we've got rid of all that horrible bright stellar light in the middle, and we've managed to uncover this planet and detect it directly in the image. And you can also see, because of this pyKLIP process, a lot of these like sort of maybe more noisy effects kind of disappear just in the medium processing and the algorithm itself, as it realizes those pixels aren't representative of the actual astrophysical scene. So before I show you exactly how that's done, I do want to give you a note on image registration. So before we do that PSF subtraction, it's good to know, what is the precise location of the star in this image. It just looks like a blob to us. And even if you change the scaling, you want to get like a precise measurement really to the subpixel level of where the star is in this image. It's important to get that PSF subtraction right, because you might imagine, if the center of your reference image is slightly off from the center of your target image, then you're going to be subtracting the wrong pixel from the wrong pixel in the relative images. And additionally, your astrometry might be off. If you don't know where the center of your star is, then it's harder to know relatively where the companions or other stars in the scene are. So for NearCam, in spaceKLIP, the way we do this is we compare to a WebPSF model. So we model the shape of this stellar light, and we compare it to our image itself to get the precision of the location of the star. And we can do that to roughly 6 milliarc seconds, which is about a tenth of a pixel. And then for MIRI, actually, this is a big stumbling block for us. We found it very, very difficult to use the WebPSF models to track the location of the star precisely. So instead, we just assume the centering is perfect, which isn't ideal, but we do know that the target acquisition procedure for the MIRI coronagraphy is pretty good, still to sort of maybe 10, 15 milliarc seconds. So that's still roughly, 10% of a pixel. Okay. So in this process, you have a few different parameters to tweak in pyKLIP, and these are just options that pyKLIP gives you. You can tweak the number of subsections. So this is splitting your image into different sort of radial chunks. You can split it into different annuli, so you can chunk it up this way as well, as subsections. And the idea here for both of these is, you're splitting up the image to kind of perform PSF subtraction on each chunk separately. Maybe you want to do this because you think, that the PSF subtraction in one region is different to that in a different region. Personally, for myself, I found for the JWST observations that just one subsection and one annulus, i.e. the whole image, is totally fine to use, and I haven't noticed any dramatic improvements from sort of chunking it up, but we haven't really looked in that in a significant amount of detail. You can tweak the subtraction strategy, like I said. So you have this ADI, where you rotate the target and you just subtract that away to try and recover the planet. You have RDI, where you just subtract this reference observation to recover the planet. And then you have ADI plus RDI, where you create some combination of the other role and the reference observation, and you subtract that combination away to leave you just behind the planet. And then finally, you can also tweak the number of PCA modes. So for those who aren't familiar with how KLIP works, this might seem a bit unusual, but essentially what it does is it breaks down those residual stellar light images into their principal components, and you can pick, how many of those principal components you want to subtract away. Sorry if that doesn't make entirely too much sense. We can discuss it later if you want, but that's sort of how this algorithm works. Okay, so I'll give you a demo of how this works. So if we go to this PSF subtraction stage here, we're doing the same thing. We're telling it, look for the CalINTs files. We're telling it, use the cleaned images. These are all background settings. This is for MIRI, so I won't touch on those right now. It has an option to blur the images. So what we found is that blurring the images can be very useful if the PSF is undersampled compared to the detector, which in the case of some of the shorter wavelength filters in the long wavelength channel is true. But I won't dig into that too much today. And then this is just whether we want to load the centers we've already found, or if we want to recompute them. We can give it what centering algorithm we want to use. This JWST pipe is kind of our tweaked version of the JWST pipeline. We have what subtraction mode we want to use, and then these different settings that I mentioned earlier. So the number of annuli, the number of subsections, and then this numBases is how many PCA modes we want to use. So we can load that all in and hit go. And while that's loading, I can show you in here, this is where it's loading, and this is slowly performing the subtraction, and it's performing the image registration as well. While that's doing that, I can show you an example here of what that image registration looks like. So it will create this ancillary file where it can create this shifts folder where it saves all the relative shifts of the different images in physical space. You know, how has the star moved in the image? And you can see for the science, you have two blobs here. You know, you have quite a cluster here for all the different integrations for one roll angle. And then at another roll angle, it looks like the star has shifted slightly and moved in the image. And then on the left here, we have, you know, what the residual is if you subtract away the first image from all of the other images before we do any sort of alignment and after we do any sort of alignment. You can also see this clearly for the reference observations. So here the reference observations of, sorry, this overlaps the legend, has happened in sort of 9 different positions here, and this has tracked that change over time for each of the different integrations, and you can see how it's managed to really knock down the residuals by shifting everything around to the right location, so they're all to a rough common center. So that's going to tick away doing the subtraction now, but while we're waiting, I can just show you one that I've done earlier. So it will just create this save of the meta file so you can look at it later. And you can also see the file is sort of named by the date. So it will tell you, you know, you ran this on this date, this was the subtraction method you used, how many annuli and subsections you used, and what run it was if you perform this multiple times. And then this is what our subtracted image would look like. And you can see here we have the image of the planet. If I change the scaling, maybe something like that, you can see here's the planet there, and we've got some background sources too. Okay, so that's ticking away now. I don't think there's any need for us to sort of wait for it.